Okay, I guess we waited long enough, so
Oh, did you print out the bio? Oh, I have
oh
it
no,
somewhere here.
I have not. So this is your mic. Okay, with introducing.
Yeah, I'll introduce.
Do I get a mic though?
Yeah.
Yeah,
Oh,
because the people on, because we have several people online and they need to hear you.
Yes, as close to your mouth as possible. This.
We can hear you fine without the mic if that's.
Oh, I guess if you don't want to use a mic, you don't have to, because they said the online people can hear you.
Okay, yeah. So
You prefer not to have it?
it's okay the way.
Okay.
Yeah.
So this is already on.
Yeah.
Yeah, I'm
Oh.
just not sure if you get feedback with the mic.
Okay, we'll try it without the mic. Okay, hi everyone. This is Mukul
Bhattacharya.
Bhattacharya, sorry. He's an Eberly postdoctoral scholar at Penn State, working with Kota Marase and David Radishe.
Correct.
Prior to this, he was a grad student at UT Austin from 2015 to 2020, where he worked with Pawan Kumar. His work broadly involves the detailed modeling of radiative and dynamical processes that occur in high energy transients, which subsequently led to observable multi-messenger emission, electromagnetic, cosmic ray, neutrinos, and gravitational waves. In particular, he's exploring magnetized outflows as the sites of R-process nucleosynthesis and subsequent kilonova neutrino emission, using AGN observations from Seyfert galaxies to explain the missing connection between TeV neutrino flux and diffuse gamma ray background, and studying the magnetized NSs as potential sources of coherent radio emission observed for FRBs. Okay, thank you so much for coming here, and
Thanks a lot for the nice introduction.
Yeah.
Probably I can just use this one.
Yeah. You can just,
Please let me know if you have any trouble hearing me. And thanks a lot for your patience. So as the title says, today I'll be talking about nucleosynthesis and outflows, predominantly magnetized outflows from core collapse or binary mergers. And also if we can see kilonovae and high energy neutrinos from these sources. So here are a list of my collaborators at Penn State and Virginia Tech, who most of this work has been done with. And I would like to thank them to start out. So regarding the origin of nuclei, we know that light nuclei were generated really very close to right after the Big Bang happened. There was the equilibrium electron fraction, which is really the ratio of electrons or protons to the total number of electrons and protons combined. And it was roughly half, which means we had equal number of neutrons and protons, but just because protons are lighter, some of the neutrons decay into protons. And we eventually got an electron fraction of 7/8. And we can explain the abundance of hydrogen and helium with that. We have about 3/4 of hydrogen, 1/4 of helium in universe. So that's fine. But how do we get nuclei that are heavier than hydrogen and helium? We know that in stars like our own sun, there's nuclear fusion. So there's more and more material fusing until we reach iron, which is the most stable nuclei. And it isn't really viable for fusion to go anything beyond that and synthesize nuclei that are heavier. And once we get nuclei up to iron, we can have events such as supernovae, flares, or pulsations, which can enrich the universe with those nuclei. But my work has been to see how do we get any nuclei that are heavier than iron. And predominantly, there are two processes that have been looked at in literature. One of them is called slow process, S process, but I'm going to focus on R process, which is the rapid neutron capture process. So if you look at this animation, the x-axis is the number of neutrons. You can't see it here, but it's the number of neutrons versus the number of protons. And the time is going from 0.5 seconds to about 100 seconds, but most of the nucleosynthesis happens in the first second itself. The color coding means if you have more of red, the nuclei is more abundant, versus blue, it's not synthesized as much. So how it goes is, first you capture free neutrons in the system, so the curve moves to the right. And then eventually everything decays back to what we call the stability valley that's shown in the dark color. And that's due to beta decay and eventually a stable neutron to proton ratio. But what stands out is there are three different peaks, first, second, and third R process peaks, which are mass numbers 90, 130, and 180. where the abundance is higher than it's anywhere else. And this is a very rapid process in the sense we get about 100 neutron capture events per second, whereas in slow neutron capture process, it's just one every few decades. And to zero in on the candidates where neutron capture can happen efficiently, we have to look at sources that have, one, a lot of free neutrons. These neutrons have to be captured very rapidly in the system. And the medium has to be dense and hot, because if it's not, then it's not efficient for nucleosynthesis to happen. In a colder system, nuclei do not interact as much. So there are these three candidates. I'll start with core collapse supernovae, which we looked at with the most detail. So if you're looking at the left panel, there's a neutron star with a radius of approximately 10 kilometers. The x-axis is the mass axis. It tells you if you're evolving the outflow radially, how much mass are you synthesizing at each radius or at each shell? As you're going from 10 kilometers to about 10 to the 4 or 10 to the 5 kilometer, initially you would have intermediate nuclei like beryllium, carbon synthesized from neutrons, protons, and alpha particles. And beryllium, carbon, and other intermediate nuclei act as seeds and capture onto more neutrons to give you even heavier nuclei, such as nickel, silicon, etc. But if you were to evolve for longer, you can even get iron, but not much beyond that. If one were to zoom out even more to look at the neutron star, the picture looks like that. There's a neutron star at the center. It has a magnetic field axis, it has a rotation axis, but they are not aligned with each other. And there's a mass outflow rate, which depends on the neutrino luminosity, the energy, radius, and mass of the neutron star. And there are certain prefactors. The first one depends on how large the magnetic field is. So if there's a large magnetic field, there's a smaller fraction of the magnetosphere which is open to magnetic field lines. So all we care about is what fraction of magnetosphere has open magnetic field lines, because only that is carrying particles outward. And there's the F centrifugal factor, which scales up for rapid rotation. So if you get more and more millisecond kind of rotation, there's more mass that is slung out, and more so in the equatorial plane. So once we have an idea about the mass loss rate, the next thing is how can we model the nucleosynthesis in these outflows? So we start looking at a nuclear reaction network. All that needs is density and temperature for each trajectory in which the particles are evolving, and also the electron fraction, which tells us how many neutrons are there in the outflow relative to the number of electrons. Once the density and temperature are high enough, nucleosynthesis starts, and how far it progresses is determined by how small the electron fraction is. This library is pretty extensive in the sense that there are about 8,000 nuclei, including all isotopes, and about 100,000 reactions. And we can get precise predictions for the abundances of nuclei, which look like this. So there are two panels here. In the first one, we fix the electron fraction. So we are looking at a fixed fraction of neutrons in the outflow. Electron fraction is 0.45, neutron fraction is 0.55. And we are just varying the time between 4 snapshots. So initially we fix the time at 0.5 seconds from the time of core collapse. Then we stop the simulations at the breakout time, which is about 10-15 seconds from the time of core collapse. The photo disintegration time, which is about 30 to 50 seconds from the time of core collapse, and the time where the nuclei get to their maximum energy, which is about 10 to the 20, 10 to the 21 eV, and that's 70 seconds. So it's eventually longer and longer. What we see is if we let the outflow evolve for long enough, there are more heavier nuclei that are synthesized eventually. You can see the peak moves from about mass number of 60, which is iron, to almost 90, which is the first star process peak. And if you let it evolve for longer, it can go up to 130, but not beyond. It stops there and there's a turnover because these nuclei also disintegrate very quickly. And if we were to fix the time to about 70 seconds, but only change the electron fraction, as we would expect for a smaller electron fraction or for a larger neutron fraction correspondingly, you would get a longer tail in the abundance, which means there are more heavier nuclei getting synthesized, but you're still not going above the first star process peak. Before going to mergers and talking about that, we also wanted to look at if these nuclei can become cosmic rays because they are accelerated within the outflow. In this plot, the left axis is for the maximum energy to which the nuclei can be accelerated to, and the time is time from core collapse. The solid lines are for the maximum energy. So you can see that the nuclei typically start from 10 to the 18 EV or so of energy, but they are then accelerated to 10 to the 20 EV or more eventually over the first 20, 30 seconds. And then the nuclei cool off because of adiabatic expansion. So the first branch is a computation between the acceleration due to magnetic dissipation and synchrotron cooling, and these two terms basically. And the second branch is a computation between acceleration and the dynamical expansion. So what we notice is if we were to put the survival of the nuclei in the picture and look at the optical depth of whether the nuclei can survive photodisintegration or not, we would get these dashed lines. And if the optical depth for photodisintegration drops below 1, which is here, that means we have nuclei surviving as well as getting accelerated. So there's a part in between this white region where we have nuclei surviving and they are also accelerated to very high energies, which is cosmic ray energies. And not surprisingly, that's also the time we can see gamma ray emission from these progenitors. So it's a really good multi-messenger window to look at for outflows from magnetars. But we didn't see nucleosynthesis beyond the first R process peak for collapsars, which are here on the right. If they are purely thermal driven or neutrino driven, then they are more isotropic, like the green circle here. And if it's magnetorotational, which we were looking at, they are more collimated. But still, we do not go beyond mass number of 90 or 100. So we started looking at mergers where the ejecta distribution looks something like this. You have dynamical ejecta on the equatorial plane. This is specifically for black hole neutron star merger. So we have dynamical ejecta on the equatorial plane, and then there's wind, which is isotropic. And both of these are significantly more neutron rich. The electron fraction is 0.1 to 0.2 here, 0.3 to 0.4 here, compared to somewhat larger values for the collapsar ejecta. And the expansion time scale and the entropy is somewhat comparable. But we wanted to see how much the drop in electron fraction can do, because there's far more neutron-rich ejecta in the dynamical ejecta of mergers. Can it give us second and third R process nuclei? So we went back to the nuclear reaction network and plugged in these values. We just don't need the electron fraction. We need the expansion time scale, the entropy, how much mass is going into the ejecta for each of the components, dynamical and wind for BNS, PHNS, and core collapse supernovae. And these numbers are coming from numerical relativity simulations that people have done for long enough now. They have been revised, so there's some uncertainty in the values, but our fiducial values were taken to be based on where the peak of each of these distributions lie. And once we give that to the nuclear reaction network, it gives us back the abundance, which looks like this. For dynamical ejecta, in the left panel, we see that now we are getting the second and third R process peak with lanthanides in the middle and with actinides at higher mass numbers, which we were not getting just with the wind ejecta, which is the right picture here. So in the right, we had core collapse supernovae, which we looked at. It was stopping at mass number of 90 or going to 130 at most, which is the second R process peak. But to get to anything further, this seems to tell us that we need dynamical ejecta from mergers, or else we don't have enough of them. And we wanted to compare this with observations. So we looked at solar abundance data, and that from a ultra metal poor star, which is shown in purple circles here. And we wanted to see if we were to add up the contribution from each of these sources, binary neutron star, black hole neutron star, and core collapse supernovae, then which are the mass number ranges where the abundances from these events dominate and how. So what we see is core collapse supernovae contribution dominates up to a mass number of 100 or 110. So initially, the blue curve here gives most of the nuclei that are intermediate in mass. But if you are to look at nuclei that are heavier in mass than atomic number of 55 or 60, then you have to get them from mergers. It's either the red curve or the blue curve. It's also uncertain because the rates of these events are somewhat uncertain, and we don't know them very well from observations. They are not very well constrained or from the simulations. But qualitatively, it seems to tell us that heavier nuclei have to come more and more from mergers, and intermediate are coming from core collapse. And a natural implication of looking at nucleosynthesis is not all of these R process nuclei that are generated are going to be stable. The unstable nuclei are going to decay, and as they decay, they can power kilonovae. And the question is, can we actually see them? Because we can have gravitational wave triggers, and if we have triggers with O4, does that make sense to kind of follow up BNS or BHNS mergers to look at the kilonova, and are they even bright enough for us to see? So there are really two components. There's the red kilonova component from the dynamical ejecta, the blue from the wind, and they look somewhat different for BNS versus BHNS. For BHNS, the light curve is far more broader, so we have much more chance of observing it. And 24.7 is close to the magnitude of LSST. So we are seeing we can capture both the components for BNS, but there's a chance we miss the lesser bright red component, which is coming from the dynamical ejecta for BHNS. But this again depends a lot on what the uncertainty in the mass is and the composition measurements are, which we don't have very good handles on. So we wanted to derive the number of BNS and BHNS events that we would see if we get a trigger from LIGO 04, and if LSST was working in conjunction, which it is not, it will come up next year. How many events can we get like this? And it's typically about close to 10 BNS events versus order unity BHNS events. So we should be seeing them, but a lot depends on how what the uncertainties are in the kilonova light curve modeling, which are improving when we get more detections eventually. This is the last part that I wanted to talk about. So it's just not the kilonova, there's also neutrinos, and they are potentially a cleaner multi-messenger to study just because they do not interact with the matter as much. So gamma rays, neutrinos, and cosmic rays are getting originated from the same source, which are magnetars. Cosmic rays are deflected a lot because they deflect with magnetic field. Neutrinos are not. They don't interact with matter as much either. So these are magnetized outflows. There's magnetic dissipation that happens, which energizes the particles, but it also breaks them down. Nuclei are broken down to neutrons and protons, and these protons interact with photons, which are within the jet, and they are very high number densities. So nuclei and photons combine to give pions, which eventually decay and give neutrinos. And these neutrinos can be very high energies. We find that these can be 1 TeV or more. For comparison, supernovae neutrinos are just MeV energy scale. So this is 6 orders of magnitude energy higher. And we wanted to see how the neutrino fluence looks like, which is the time integrated flux. And we looked at it for 3 different progenitors, Wolf-Rayets, blue supergiants, and red supergiants, and for 3 different configurations of the central magnetar. And we see that for Wolf-Rayet, the neutrino emission is always attenuated very quickly in energy. So we do not go beyond, we are starting from TeV, but we are not going beyond 10 or 100 TeV. But for blue supergiant and red supergiants, which are far more extended and less dense as a result, there isn't as much inverse Compton cooling or attenuation to really kill the signal so early. So we should be seeing neutrinos at PeV energies, for example, really high energies, but that also depends on how energetic the neutron star itself is. So the solid line peaks slightly later compared to the dotted line, which is lesser energetic system. And eventually we wanted to see how many events would we detect. So for that, we have to integrate the flux with the effective area of the detector. And in this case, it's IceCube generation 2, because IceCube is more sensitive on GeV energy scales, not so much TeV. Once we integrate and get the numbers, it looks like for blue supergiant and red supergiant progenitors, we can get tens of events in neutrinos, which are 1 TeV in energy or more. Of course, this scales with the source distance. We have assumed 10 megaparsec here. It should go as 1 over d squared, depending on if it's smaller or larger. But it just tells us that Wolf-Rayets are not as promising in terms of seeing neutrinos, but supergiants are. And I think I'm pretty much close to the 20-minute mark. So I'll try to wrap up with that. What I had there is, first we looked at nucleosynthesis, and we found that magnetized outflows have more promise in terms of generating heavier nuclei, much heavier than iron. And that's because their large magnetic fields and rapid rotation actually helps to lower the entropy. So physically, if you think of it, there's more energy in magnetic fields, which is taking away energy from the thermal or the kinetic energy of the outflow, which makes it easier for the neutrons to get captured by the seed nuclei. They're not as energetic, and nucleosynthesis to progress further. There's chances of seeing cosmic rays because these nuclei are also getting accelerated to very high energies, 10 to the 20 eV or more. and they're also surviving, but there's a very special window where we have to look at about 20 to 50 seconds from the time of core collapse. And for our process, in collapsars, we only get up to the first R process peak or slightly beyond, which is mass number of 90 or 100. But we need mergers to get nuclei that are mass numbers 120, 130, or even close to 200, second, third peak, lanthanides and actinides. And finally, neutrinos should be produced in these systems. They are far more energetic than what we see in supernovae even. And we can see tens of events for extended sources such as supergiants, blue or red. But if it's a far more compact source like wolfrads, which are thought to be main progenitors for GRBs, by the way, we should not be seeing as many neutrinos for a typical source at 100 megaparsec, for example. Yeah, with that, I'd like to thank all of you and would be happy to take any questions. Thank you.
Turn on the lights.
Yeah.
Let's see if there's any. If anyone online has questions, sorry.
Oh, I
feel-
think you.
Oops.
Okay.
If anyone online has questions, please feel
Okay,
free
let's see.
to. No, I think we are good with screen.
With the screen.
Any questions from?
It's just
I-
us.
Yeah, no, I think we should probably put this back.
Yeah.
Okay.
I have a question.
Yeah.
Sorry.
Don't you expect neutrinos also from mergers only from core collapse?
This is for core collapse, but we can have them for mergers. What you need is particle acceleration has to be efficient enough, because if you are not crossing the pion production threshold, which is a few tenths of MeV to a GeV, you wouldn't eventually get the neutrinos. That happens more readily in collapsars than in merger outflows.
So you need a sort of jet form, right?
You do need the jet. So these neutrinos are getting produced in relativistic jets from
Okay.
collapsars, which you can also get from mergers. You just need them to be energetic enough.
Because you know, so
Yeah.
we observe GRBs from also these
Yeah.
merger systems. So
Short GRBs, yes. So there would be neutrinos from those systems. We haven't detected them yet. It has to do a lot with directionality because we should be looking close to the opening angle of the jet, and we don't always see it.
So you expect
But
an emission, not jet from neutrinos out of core collapse supernova, while you expect something along the jet.
yes, yeah. So if I actually had that slide, I don't know. I think it is this one. So if we are looking at the jet and the neutrino production, it looks something like this. You have the jet, there's a cocoon around it, but most of the neutrinos are really getting out close to the head of the jet. And it depends whether the jet is collimated or not. If it's not if it's uncollimated, then there's just larger cross section through which neutrinos can come out. So, but it would be for both pictures, yes, not just collapsars. Right. Thank you.
This is not exactly a question, but I was really surprised that you said that you could, this is not my field of expertise, but I was very surprised that you said you'd be able to detect these from blue and red supergiants even at distances of 100 megaparsecs.
Yeah.
So I guess, what is the main rate driving factor? Is it just that we need the jet orientation to be right in order to see it, or?
Yeah, we need the jet orientation to be, we need the jet to be one, energetic enough,
Okay.
and we need the medium to be,
pretty rare.
yeah, that's already. So when I'm talking about millisecond, like 1 or 2 millisecond magnetars, or 10 to the 15 Gauss or more magnetic field magnetars, that's already like 1% or less of the total number of core collapse events that we're looking at. So how we would want to do this better is to actually include a population of magnetars weighed with the magnetic field and the spin period to see how many events actually look that extreme with very high fields and rapid rotations. Most of them wouldn't be. It's a probability distribution. It's basically a population that has to be included and seen if these numbers would be normalized. So what I'm saying is, if you're looking at 10 to the 16, 1 milliseconds, this is normalized by a weighting factor, which is smaller compared to what it is at smaller fields and less rapid rotation, because these are likely to be more in nature.
I see.
So these are kind of extremal rates that we are deriving here.
Okay.
We just don't know the population very well at this point, at least for this range in magnetic field and spin period. We don't know the distribution as well. We haven't really detected a lot of these magnetars with such high BNP yet.
Yeah, that was just very surprising to me.
Yeah,
Like
it is
seeing
kind
any
of pushing that.
sources from any individual stars at that
Mhm.
distance is pretty crazy.
Yeah.
Okay, wow. So if you detected fewer, like more or less of these neutrinos from red and blue supergiants, would that change your models in a significant way? Would you be able to identify like whether or not you're actually able to see things farther away?
Yeah, so it
Like,
would reduce the distance horizon up to which we can
Okay.
have as many highly energetic neutrino events detectable. So it wouldn't be, for example, 100 megaparsec. It would fall down. It scales as a function of t squared. So it would probably be closer to 10 megaparsec if we do not have as many 10 to the 16, but more 10 to the 15 or 10 to the 14 Gauss magnetars. So this distance was just a reference distance for us to look at GRB progenitors and typical GRB progenitors at tens of megaparsec. But it might be that they are not as common at that distance anyway, and we are not expecting to see them as a result.
Okay, that
Yeah.
makes sense. Yeah.
Sure. Thank you.
Any other questions? Any online? Just checking in case we. Okay, well, I think he still has
That's
some
it.
slots and he's actually around tomorrow too. So if you guys
Yeah.
also want to meet with him tomorrow,
Excellent.
that would be great. Thank you everyone for attending. Sorry about the delay, but I really appreciate it.
Thank you so much. Thanks.